Okay, so from Tuesday.
0 and half.
Okay,
Two.
so what's the answer to the first one?
0.
0. How come?
It's the x, there's only one x on the bottom, once you do all the things.
Okay, if you look at the ratio of the dominant terms as x gets huge, right? X approaches positive or negative infinity. The bottom is a bigger power of x, so it more aggressively goes to infinity, right? And so we get 0, right? And so that's what's cool about that is the left and right tails of the function both share the same horizontal asymptote at y equals 0. Okay. What about this one right here?
-2.
Equals, the answer is -2. Good. And once again, what's our reasoning for that?
Because the x's cancel out
Good.
or the twos.
Good. So if we have the limit of a rational function where the polynomials are the same order, top and bottom, then we just take the ratio of the leading coefficients, right? So we get -2. And once again, this means that if we were to graph both tails, they're both going to approach y equals -2. We don't know what's going on in there until we investigate more closely, right? But the tails, we know that they're going to stick to those horizontal asymptotes, right, in the end behavior, okay? All right, what about this guy? What about as I approach positive infinity? What am I going to get? Okay, yeah, it's undefined, but we can do better than that. We can do better than that. What could we say here? If we look at the ratio of the leading terms, as x approaches positive infinity, what's the magnitude of our answer going to be? You told me it's undefined. By that you meant probably what?
Vertical asymptote.
It's not a vertical asymptote necessarily, but it is exploding,
Yeah.
right? So we know the magnitude is going to be infinity. We just need to know the sign to know if it's exploding up or down, right? Well, let's just see, what would we get?
Positive.
If I'm approaching a positive number, what sign am I going to get on the top? Negative. And on the bottom, I'm going to get positive. Negative over positive is negative. So as x approaches infinity, f of x approaches negative infinity, right? Okay, what about, same thing now, limit of f of x as x approaches negative infinity. She's not here. Okay, so once again, we know that because the top is a higher order polynomial, we know that the magnitude is infinite, but what's the sign going to be this time? It's going to be positive, because as x approaches a negative number, -2 times negative number cubed is going to be negative times negative is positive. Bottom is going to be positive, right? Because it's an even power. And so we get plus.
Even if it was an odd power, wouldn't we have simplified it and be using the simplified version? In which there wouldn't even be an x on the bottom? Or no?
Well, you could. It's fine.
But that would change.
But you don't really need to, right? You don't really need to. All you need to do when you're inspecting this to get the end behavior, you just know that 3 is bigger than 2, so it's infinite. And then I'm just going to find sine top, sine bottom. You know, as in SIGN, sine top, and SIGN, sine bottom for the overall sign of that.
And you have to use the original thing, not the simplified.
It doesn't matter, if you use a simplified one, I'm gonna get the same answer, because if I divide top and bottom by x squared, I'm gonna get -2 times x to the 1, that's gonna give me positive on the top and positive on the bottom.
But if the bottom was cubed, then it would make the bottom negative on the original.
Right.
But on the factor, it would be positive.
Right, but then if the bottom sign changes, then the top sign would change also.
And then that could be another negative, could be 5.
Right,
Or,
so,
and then it would be, oh, never mind, yeah.
you see what I'm saying? But to play it safe,
Uh-huh.
why simplify? You don't need to,
No.
right? Okay, so then what does that tell us? Well, that just tells us that, the end behavior is doing this stuff, which is useful when we're trying to make a sketch of all this, right? Okay, and that's what we'll kind of do in section 3.6, is we pull all this stuff together and tableify it, even this end behavior stuff, right? Okay, so what about something like, say, this guy?
And it still approach 0.
How come?
X is negative 1 for X.
The answer's still 0. Why though?
Because the top is becoming smaller, and then when you take the sign of it, it becomes even smaller.
Okay. Right, the top is, sine of 1 over x is approaching, 1 over x approaches 0, right? And so it approaches that we're taking the sine, but do I even care? I don't even really care, I don't even have to think that hard, because it's the sine of something, right? So who cares? What's the biggest that a sine value can be, the output of sine? What's the smallest it can be? No. -1, right? So it's gonna oscillate between -1 and 1, well, big deal, bottom's getting infinitely big, right? So even though the top of the fraction is not constant, it's bounded, right? It's bounded to have values between -1 and 1 inclusive, right? And so the bottom is still exploding while the top is not. And so the answer is 0, right? Make sense? Okay. How about this?
Could you still take the biggest
Well,
X and square?
Still be 0 because it's just subtracting -1 to 1, so it doesn't matter.
Yeah, so it's 0, because once again, what's the dominant term on the top? The x cubed, right? The sine x, who cares? That's small, right? This is big, and so if I look at the ratio of the leading terms, bottom is still bigger, so it goes to 0. Okay? All right, how about something like this?
So is it when the bottom is, whenever the bottom's biggest, it goes to 0, whenever the top is biggest, it goes undefined, but whenever they're equal, it goes to whatever it equals to.
The ratio of the leading coefficients. Right, right. Okay, so we've looked at just about every interesting case that we're going to consider. Here's one more, though. How about that one? Actually, I'm just gonna take them one at a time. Let's just take positive infinity to start with. Sure. What do you think about that one?
Undefined. Because,
A little strange, right? Looks a little strange. What about, talk to me about that bottom function. Bottom one, it's not strictly a rational function, because the bottom's not a polynomial, right?
for the positive, wouldn't you be able to, change it to the parentheses, the -2? Instead of that being square rooted? Or,
It is square rooted. But,
If you're going towards positive infinity, there's nothing that's gonna make it, I don't think so. There's nothing that's gonna make it 0 on the bottom.
right, right. So we're not gonna get that, that's not gonna be an issue. Now, if you look at that bottom function, there are two terms inside the square root, right? As x approaches infinity, which of those two terms is clearly gonna dominate? The 2x squared, right? The 1 is just gonna drop out completely as x approaches infinity, right? And this is gonna look like, this is gonna be equal to the limit of 3x, because that's the dominant term on top, right? Divided by the square root of 2x squared. Agreed?
which makes it be 3/2.
Okay. And so, what's that? So I could rewrite that as the limit of 3x over, I could write that as the square root of 2 times the square root of x squared, right? On the bottom? Does everybody agree? Okay, as x approaches infinity. What is the square root of x squared? No? Okay, sort of. It's the definition of a function. Think about that. The square root of x squared. If I square x, what's that do to the sign? Makes it positive. And then if I square root it, I get back a positive answer. Even if x had a negative value to begin with. So what's that sound like? What was it?
It's the absolute value.
Absolute value. Yeah, that is the definition of absolute value of x. Okay? Right? Now, this is a pretty sweet little function here. I use this a lot when I program, actually. What is x divided by the absolute value of x? What's that going to give me back as an answer? 1 or, let's say, what if x is 4? If x is 4, then the absolute value of x is 4, right? 4 divided by 4 is 1, right? Does that make sense?
Yeah.
Okay, what if x is negative 4? What's the absolute value of x? 4, so then I get negative 4 over 4 is negative 1, right? So what this does, like when I program problems for my, when I'm building math problems, a lot of times you'll want to say, okay, well, maybe I want to do the opposite sign of what this term, of what its sign was, right? So how could I say that? If x is a variable that could have both positive and negative values, couldn't I just do something like negative x over the absolute value of x times, let's just say that was some variable a, right? Times a. That's going to give me back whatever the sign of that was. See what I'm saying? Right? Or times, I guess I called it x, didn't I? Not a. Right? All that's going to do is change the sign, right? You see what I'm getting at? You can do tricky stuff like that. So it really is kind of a cool, it does something interesting. What it gives you back, x divided by the square root of x, just gives you back the sign of x, doesn't it? Right? It's either positive or negative 1, right? The sign. Okay. What if I graph that function? Well, what's that doing? As x approaches infinity, let's just graph the function x over the absolute value of x or the reciprocal. Makes no difference, same thing, right? Doesn't it just do this? Right? Everybody agree? Okay. So as x approaches infinity, what's the value of that going to be? 1. X is positive then, right? If x is positive, this ratio is just 1, and so my answer is just 3 over root 2. Right? You see that? So what if we want to approach, what's going to be then the limit of 3x over square root of 2 absolute value of x as x approaches negative infinity? Yeah, so then that's going to be, when x is negative, that gives me back the sign of x, which is negative 1, right, times 3 over root 2, right? Technically, I should rationalize the denominator and multiply square root, top and bottom by square root of 2, but same number, right? Make sense? Okay. So see if you can do one of these in your head.
Will you help us?
No, I'm not.
Mental math.
That's a hard pass.
So what if we have, so what do we get? Yeah, so I'm going to get back the limit of negative 3 x over absolute value of x, aren't I? Right? As x approaches plus or minus infinity. Right? So there's that funky function that gives you back the sign of the input. Right? And so what do I get? In the case that x is positive, I get back negative 3. in the case that x is negative, I get back,
Positive.
so I get that, don't I? So the limit as x approaches positive or negative infinity comes back as negative or positive 3. Right? Got it? No big deal. Okay. One more. You get this. You're good.
Mental math, Michelle. Mental math. Got an example in my brain.
Is it positive or negative 2?
Hmm?
Is it positive or negative
Would it
2?
be positive, negative, or
Positive or negative?
Oh, 9 halves.
positive or negative 3
No,
halves?
it'd be,
3 halves.
or would it be negative
So I'm just looking at these terms, right? That term and that term. What's the top one simplified to?
3. 3, that's the value of x.
or over negative
Right? There's my sign extractor, right? And so we end up with
There's too many sign words.
negative or positive
It was
3 halves.
Wouldn't it be positive or negative 3 halves?
No,
Because when it's
Oh.
positive, it's negative.
right?
Come on, River.
Does it really matter how we say
Because
it?
when x is positive, I'm multiplying by a negative fraction, so I get back, see what I'm saying? Okay? Good. Good, good. All right, so then what I wanna do, last one.
Wait, but
You
we're
said
good.
we're good.
So we are
got
good,
it.
we are good for that section. So now I just wanna show you how to pull this into.
In 6.
How much time we got here?
Got like 28 minutes.
So much time, we could kill it.
Exactly, so much.
Usually that happens when we're like 3 minutes
Hey, Rick.
left.
Can you go pull the car alarm?
Why would
He
you do
has
that right
sport
before
over
lunch?
us.
Pull up with my money. Cause then we get more lunch.
Go
No, you'll
outside.
pull
Yeah, what are they gonna do? We're gonna go
Your
outside,
GPA
they're gonna
pull
hold
it
us there?
They probably would, actually.
Yeah.
In our school, they probably would. I wouldn't.
Wait, I ate lunch here, so
Ah.
that's why you need a car.
Yeah, we'll be laughing when we're leaving.
That's why you need a car.
Let's go.
Hey, I'll let you go down the 6 roads. Just
You're really good at going downhill.
roller coaster. Get to an uphill and you're just like slow sliding backwards.
Shitty.
Yeah. Splash.
Okay. I'm just glad they didn't clear out any of the snow, you know?
Okay, find everything. That's what I want, I want it all.
As a
You
group,
can't get everything out of that, there's no Eve.
No, we can get everything.
as
We
a
get
group
everything.
where we can use the board.
Oh, we'll just, we'll go through it as a group, we'll just walk through this one, but we could get everything we've talked about on our table now,
Alright,
okay?
well, let's start with the table, get the first, second group.
Okay, so what's our domain? All real numbers except
For 4.
Okay, so x cannot equal 4, okay, good.
Oh, there's the Eve.
Okay. So then we need some derivatives, right? So what's y prime gonna be? Kind of.
It'll be x squared minus 6x plus 12 times by 1.
Okay, by quotient rule, right, times derivative of the bottom, which is,
1.
hold it, hang on, no.
Ludi high.
Lodi high.
Ah,
Oh my
sorry,
God,
it's
you
x over 4
Jeez.
times
X
by.
minus 4.
Times,
Okay, remember, why don't you solve the equation?
times what?
Do
Actually, that's easier to decide.
get your participation points, come on.
minus
Now.
times
One.
divided by, there we go. Okay, so if we, let's go ahead and do some algebra here. So if we expand this out, that's gonna give us 2x squared, but we're gonna subtract an x squared, so an x squared. We're gonna get minus 6x minus 8x is minus 14x plus 6x, minus 8x, right? And we're gonna get positive 24 minus 12, right? Okay, all divided by x minus 4 squared. Okay? All right, so okay,
Now,
so
what-
then,
Second derivative,
Now, second derivative, letter by.
okay, we gotta find critical numbers though while we're at it. How about?
letter calculus.
Okay, so where are the critical numbers of the first derivative? Okay, so do we get a critical number then at x equals 4?
Yeah. No.
Wait,
I thought,
yeah, yeah.
I think so.
Say that again, 4?
Why wouldn't it be x equals 4? Because it doesn't exist, I guess, but.
Oh,
Okay,
it's
so-
undefined.
Be undefined.
Oh my.
So it's nothing.
Exists, but.
So that is not a critical number, because critical numbers are only interesting where the function is defined, right? So, right? So remember we talked about that as being a function, the successive derivatives of a function always inherit the vertical asymptotes of the function, right? So the parents always are gonna pass on vertical asymptotes, right? So that's not a critical number because the function is not defined there, okay? But we are gonna get critical numbers where it equals 0. So y prime equals 0 when x equals what?
6 and 2.
6 and 2, everybody agree? Because we could write that when x squared minus 8x plus 12, which factors into x minus 6 times x minus 2 equals 0, right? So therefore, when x equals 2 or 6. Okay? Second derivative. Okay, so we're gonna get what? X minus 4 squared times
2x minus 8.
minus the top times derivative of the bottom, which is right divided by bottom squared makes it to the fourth. Okay. So then that's equal to.
Hey, we can pull out 1x minus 4.
Oh boy, that's gonna be kind of, yeah, we could factor out an x minus 4, that's good, right?
Could we also
can-
pull out a 2?
Yes, we could. Let's take out a 2 times the quantity x minus 4, leaving us with,
Technically less stuff.
well, that's actually leaving us with on the top x minus 4 squared, isn't it? Because that is 2 times x minus 4 right there, isn't it?
Yeah.
Right? So that's gonna leave us with x squared minus 8x plus 16 minus, and then that stuff just goes away, right? Minus the quantity x squared
Yeah, where'd you get that?
minus 8x.
Wait, 16 is supposed to be, wait,
Isn't that supposed to be 12?
no, it's supposed to be,
Is it really supposed to work out that well?
x,
It will,
wait, is it?
Where does the 16 come from?
because of this.
Because 2 times 8, duh.
Wait.
Because
why
that's what I factored out, right? I factored out the red stuff went out
Why,
front.
why did you expand?
So what's the
Oh.
quantity? Well, because I want to be able to combine like
Yeah,
terms,
that includes.
Yeah.
Yep.
right? So the quantity x minus 4 squared just becomes that.
Yeah.
Okay? And that whole thing is divided by x minus 4 to the fourth, so I'll cancel one of those.
Why wouldn't we just take out all three x minus fours?
Yeah. Just
What do you mean?
Because you can cancel for
X minus 4 squared.
But there's
plus
no
the
more
other
x minus fours on that,
I
so,
only have one to extract from this term.
yeah.
But you,
And what's the first one? Why didn't you do anything with that one?
Well, I did. I
That's
took
the
out,
one that he pulled
you
out.
guys told me to factor out 2 times x minus 4.
Okay.
That just happens to be 2 times x minus 4. So I'm gonna factor all that stuff out front. There it is. What am I left with? Well, I'm left with this and
Good job, man.
that, right?
Yeah.
Okay, let me pause here. Does that make sense?
Yeah.
Okay.
You can get rid of the x squareds.
So then that's equal to, see the x squareds cancel and the
Or
8x's cancel. So I get 16 minus 12 is 4, right? So on the top, I really just end up with 2 times 4 is 8. And on the bottom, I get x minus 4 cubed.
that is the cleanest second derivative I've ever seen.
So are there any critical numbers of the second derivative? None, right? None, because
Aren't there no zeros?
there's no zeros of the numerator and there are no unique zeros of the denominator, right? The only zero of the denominator is where our function is undefined, right? Okay, so now what's really cool about this is we get to make a table out of this, and our table is going to include everything that we did. Okay, so x, y, prime, y double prime. Okay, so we'll start off with our domain, right? Our domain goes from negative infinity to infinity. However, 4 was interesting, right? At x equals 4, the function was undefined, right?
Put that 0 for the.
So what does that make it? A vertical asymptote. Okay, and that divides up our universe into separate universes now. We've got 2 completely different parts of this function that are coordinated off by this asymptote, right? Okay, so what else did we get? We got first derivative critical numbers at 2 and 6. Okay, so at 2 and 6, we got zeros of the first derivative. So where should I go now?
Test points.
Test points? What should my test points be?
And 0.
No, don't need them.
No, don't say.
2 and 6,
Oh, double prime.
right? I'll go down to my last row and kill 2 birds with 1 stone. So what's the sign of the second derivative when x is 2?
Negative.
Negative. When x is 6?
Awesome.
Positive. So what's that tell us? So this tells us we have a horizontal asymptote and downward concavity. This tells us horizontal asymptote and upward concavity, right? So that tells us relative minimum, relative maximum, right? Okay, what about end behavior? Okay, we can do that too. Let's take our end behavior. So we'll go right back up to our original function and let's do our limits at infinity. Yeah, so the limit of y as x approaches plus or minus infinity equal what? As x approaches, so here's our leading terms, right? So what's it gonna do?
It's undefined
Okay,
and it's.
when x is positive,
Undefined.
it's positive. When x is negative, it's negative, right? I'd get positive over negative,
Oh, because you just plug in the signs there.
right? Okay, so look what we can do here. How cool is this? See what I'm saying?
Oh, cause then you'll put a negative big, negative big.
How cool is that?
That's super cool.
It's like,
Right? So now let's go ahead and anchor these points by just evaluating the original function at 2 and 6. So if I go at 2, I'm gonna get 4 minus 12 plus 12. So I get 4 over negative 2, so negative 2. Everybody agree? At 6, we're gonna get 36 minus 36 plus, so positive 12 over 2 is 6.
I like this.
And now we can take this
Make it complete.
sweet table and we can sketch our function completely. Right?
Wait, how would it be 6?
Did I get that wrong?
that's right.
I can question that.
Okay, so it's 6, because I'd get 36 minus 36 plus 12 is 12 over 2 is 6. 6 minus,
yeah.
okay.
I should just. I had to just double check. I would rather double check than not.
No, that's good. I'm glad you do, because I make frequent mistakes. Okay, so now if we do our sketch, so here's our y-axis, right? And what's this thing look like? So at 2, 2,
2, negative
2, negative 2, we're getting
Wait,
a relative max, right?
supposed. Right.
Right? So
Okay.
there's 2, and here's 6, right? At 6, positive 6, we're getting a min, right? And we have a vertical asymptote at 4, so there's 3, 4, 5,
Relatively.
right? So then what's this thing gonna look like? So it's gonna look like, this all makes sense, doesn't it? Right? Because then we end up with this function is doing that. And on this side, it's gotta go up to positive infinity. And so it's just doing that, right? What about over here? Over
Same,
here,
upside down.
same thing but down, right? So this is a maximum, and so it's gonna move down that asymptote forever. And over here, it's just gonna continue on down forever. So that's a sketch of my function, pretty accurate sketch, right?
So for our graphing calculators, I feel like I've asked this before, but do they do that, or do they just, for every point that's on the screen, just plug that into the equation?
They do a combination of things, but they mostly,
Are they like pre-programmed with stuff, or do they just do?
yeah, they're pre-programmed with certain functions that they can just fit. Yeah. Okay, there's one other thing here. If we got time, I want to show you on this. Okay. So here's the last thing we could do. The only thing that we didn't add to our sketch that was great was what's going on with the end behavior. Okay, we knew it was infinite, but we can do one better with this. I want to show you a really cool trick. If we start with our original function here, right? So look at this, all right? Let's divide this out, okay? Let's use synthetic division. Let's divide out this rational function, right? So what's that become? It's really easy to do because we've got a linear factor on the bottom, so we can do this synthetically, right? So then we just end up with, what are my numbers, my coefficients? And what goes out front? 4. Good. So we seed the process with a 1. 4 times 1 is 4. Okay. Right? Now think what this means. So this means then that this is equal to x minus 2 plus the remainder of 4 over x minus 4, right? Okay, so in the limit, now watch how cool this is. In the limit of y as x approaches plus or minus infinity is going to be the limit of x minus 2 plus 4 over x minus 4. Okay, in that limit, this is the only term that goes to 0, right? So what are we left with? We're left with the function x minus 2. Okay, true, what we said before still holds, that as x approaches positive infinity, that's going to be positive infinity. As x approaches negative infinity, it'll be negative infinity. But this is the shape of the asymptote that dictates the end behavior. It's a slant asymptote, right? It looks like the line y equals x minus 2, right? So if we go back to our function then, we could go back to our table and we could add, because we had a situation, and we'll talk about why it occurred that way, where we were able to find out what the envelope of the function looks like on the tails, we could say we have a slant asymptote y equals, what was it, x plus 2?
Minus.
X minus 2? Okay, and so look what that does to our picture then. It tells us that negative 2 and then my slope of 1 is going to be kind of, I mean this is skewed a little bit, but it's, right, the horizontal scale is stretched out, but it should look like that. So that changes what our graph looks like just a little bit, right? We can go back down here now and do this. Right, so over here, this one's actually just gonna kind of go like that, and this one's gonna kind of go like this. Right, it's gonna gradually approach that asymptote. So that gives us a little more accurate picture, right? How did we know, looking at this picture here, how did we know that we were gonna get a slant asymptote? The asymptote was gonna be linear.
Because
Ah, good. Because the ratio, or not the top polynomial was exactly 1 order bigger than the bottom polynomial. So when we divided those out synthetically, we knew we were going to get a linear answer plus some remainder that was going to disappear, right? See how that works? So whenever you have a situation like that where the top is 1 order higher than the bottom, you can actually come up with a slant asymptote. Okay? All right, that's a lot of good math.